Violins and cellos are beautiful instruments, right? They're quite amazing to look at. Brilliant, brilliant workmanship. Somebody cut all these pieces of wood from a tree and made these instruments out of them. They sound great. They're quite amazing, but they're also very fragile little bits of wood. They break all the time. But when they're together all as they should be, they can project sound to the back of a crowded concert hall without any electronic amplification. They are very impressive little fragile bits of wood. Here's just the top of a violin. It is 4 millimeters thick or less, and it's made of spruce. It's a wonder the thing doesn't break completely. And this one is actually thinner than it should be by about half a millimeter, which is why it's so broken. And there's that old saying, tight as a fiddle string. Well, they're very tight. And then with how vigorously they get played, these little fragile bits of wood projecting sound like they do, they're under a lot of pressure. Here's a cello that just blew itself open. It just came apart. All the way down the side and all around the bottom. How does that happen? And here's a cello with its neck broke right off. This is a cello that had its neck broken off, but it's been put back together. You have to align it right so that the fingerboard ends up at the right height, the right angle. And here's a close-up of a violin being clamped back together because it blew itself apart or had to be opened up to repair a crack in the front or the back. Not all damage is so catastrophic. There's just a crack. You can see the crack right there. If this instrument is played, that crack could grow. And in the changing seasons, changing humidity and temperature, the crack could grow and just the cello could just blow itself apart. So today we're going to look at what those pressures are. How come instruments break themselves like that? And we could ask the question, why don't they break more? Because they are very delicate bits of wood. So we have to apply some physics. There's a violin, there's a spring scale that measures up to 10 newtons, almost 1,000 grams, something like that. A little ruler to measure deflection of a string. And this is how you set it up. You hook a string around the violin string so you can pull on it with the spring scale and measure how far you deflect it with the ruler. And then there's some simple physics that we'll see later to figure out the tension in the string before you deflect it. And that's also, of course, an approximation. Then we have to approximate a straight line between the end of the tailpiece and the nut of the violin and make some measurements there. We got to measure the length of the strings, the full length that comes into play in the physics of it, and the length from the bridge to one end, from the bridge to the other end. We're going to have all those measurements. So we do all those, and then we get to the physics of it, figuring out the math. We draw a sketch of what we've measured, identify where the tensions are and the force is, and it turns out that there's a simple equation. The tension in the string is equal to F times L divided by 4 times D. And those are the units shown in the little sketch. And for each string, when I did the test, those are the D, those are the distances each string was deflected away from the fingerboard. And then we did some calculations using that simple little formula. Got tension in the E string is 80 newtons, tension in the A string is 61, the D string is 56, and the G string is 52 newtons. So we add those all up, we get 249 newtons. Then we have to do a little bit more. Very similar diagram, but we're capturing different things. We're making triangles, and the one marked 25, that's 25 millimeter tall bridge. 330, that's the length of the string from the nut to the bridge. And then you can just compare triangles, do a little bit of trigonometry, and you come up with some numbers. You figure out the angles. The first angle is 4.3 degrees, the other one was 8.5. And then those tensions at those angles can be broken into two components. In this case, it's F1 and F2. One is like the horizontal component, one is the vertical component downwards, and that's the amount of force acting downwards on the bridge. We do it for the other part of the string, F1 and F2, and do a little bit of trigonometry and figure out the force on the bridge straight down from all the strings together is about 60 newtons, about 13 pounds, 6 kilograms. Well, that's like this anvil. This is a 10-pound anvil. Set that on top of the violin. That's the same pressure as is on the bridge. So there we have it. The weight of the anvil is actually less than the force on the bridge caused by the tension in the violin strings. So tight as a fiddle string, well, they're pretty tight. So we have that thin little 4mm thing. By the way, this one's been patched. Those are all pleats that patch cracks. So this very thin violin top is broken. But just think of that tiny little thing holding all that force, and this tiny little bridge holding all that force. That's just a little tiny bit of maple. Imagine that anvil sitting on top of that. That's pretty impressive. It'd be interesting to make a video of an anvil sitting on a violin top without the distributed forces, just the way a violin is made, and see what that does. Well, that's all for now. Hope you learned something and gained a new appreciation for these wonderful little instruments, these fragile bits of wood that make music all over the world.